We propose a framework for simulating filaments and their contacts with rigid bodies. A filament is represented by its node positions and edge angles and has a finite cross-section. It experiences internal elastic forces from stretching, twisting, and bending. Contact with external bodies can be modeled either as point contact or as patch contact. At each time step, we first compute the free motion velocity that would occur without contact. Next, we perform collision detection on the geometries, and then linearize the dynamics and contact constraints around the free motion velocity. The updated velocity and contact impulses are obtained as the primal and dual solutions of a convex optimization problem. This process is repeated at every time step to carry out the simulation. The figure shows the percentage of runtime spent on each computational component. We simulate a rope wrapped around a cylindrical post, with one end fixed and the other end pulled. The forces at both ends of the rope are measured, and their ratio is recorded. This experiment is repeated for multiple wrap angles. Because of friction between the rope and the post, the force ratio increases exponentially with the wrap angle. We further perform a mesh refinement study, where each rope segment spans an angle delta phi around the post. The results converge toward the theoretical predictions, confirming the accuracy of the frictional contact model. We simulate knot tightening by pulling on both ends of a rope, where the rope interleaves with itself 4 times. When compared with real-world experiments, our framework produces results that closely match the behavior of an actual rope. In contrast, a baseline method that augments the dynamics with a contact energy term fails to enforce non-penetration, causing the rope to tunnel through itself. For further comparison, we also model the rope as a chain of rigid capsules connected by springs. But this approach does not yield a physically accurate tightened configuration. Our framework can also capture an interesting phenomenon. A flat belt riding on a crowned pulley naturally self-centers. This behavior arises from the accurate modeling of patch contact, as well as the belt's internal stretching and twisting forces. In contrast, a volumetric finite element method fails to reproduce the effect. Its large element aspect ratio artificially increases the belt's bending stiffness, preventing the belt from tensioning correctly. Another application of our framework is simulating soft robotic grippers, such as an entangling filament gripper. The gripper utilizes the stochastic entanglement of filaments to grasp objects. Our framework robustly captures the contact interactions among filaments, between the filaments and the branched object, and between the filaments and the gripper base. We also simulate a bimanual robotic arm tying a shoelace. With the patch contact model, the full shoelace tying sequence is successfully reproduced. In contrast, a point contact model causes the shoelace to slip from the gripper fingers. Analyzing the pinching forces reveals that the point contact model causes large force variations, preventing stable frictional contact. For comparison, we also model the shoelace as a chain of rigid capsules connected by springs. While this approach produces visually plausible results, it exhibits high-frequency fluctuations in the internal elastic energy, an unphysical behavior since such high-frequency content naturally dissipates quickly in real materials. We simulate chains of rings suspended under gravity, and the runtime scales linearly with the number of rings. This table shows the real-time rates and scene statistics. Below is the summary. Thank you for watching.